Hello friends, let's consider this plane. Now I tell you that a line I have in mind passes through this particular point. Now I only give you this particular piece of information and nothing else. Now can you guess the line? You can give it your best, but you cannot guess the line because there can be infinite lines passing through this point. However, if I give you a second piece of information, say the slope of the line I'm thinking about or the inclination of that line, then you can actually guess which line I'm talking about because each of these lines has a different slope. Right? And this information is what we have used to write down the point slope form of an equation of a line. Now instead of the inclination or the slope as the second piece of information, what if I give you another point Q through which the line passes, which is different from the already known point P. Now in that case as well, you can actually guess which line I'm talking about because there can be one and only one line that passes through both these points. Right? And using this information about the 2 points, we have written the 2-point form of a line. So clearly from these two examples, we can tell that to describe a line geometrically, we need at least 2 pieces of information using which we can write an equation for the particular straight line. Now naturally, few questions arise. Are there other ways to describe a line so that we can write different forms of equation? Is the information about a point on the line necessary to write an equation of a line? Well, the answer to the first is yes. Of course, there are other ways to describe a line. And the answer to the second is no. The information about the point is not necessary. You can use different pieces of information to write different equations for a line. Today, we are actually going to look at a unique way of describing a line using which we are going to write a new form of equation which is called the normal form of a line. Now to understand this new way of describing a line, let's start with the circle which is centered at the origin. Now on every point on this circle, we know that we can draw one tangent and that tangent will be perpendicular to the radius at that point, right? Now if I am interested in one of these tangents, then I just need to tell you which point I am drawing the tangent from and then you'll know what line I am talking about. Or in other words, instead of describing the point, I can tell you how the radius to that point is actually inclined or what angle it makes with the positive direction of the x-axis, right? Then you'll know which line I'm talking about. So with this understanding, we can say that any line in the plane will be a tangent to a circle centered at the origin. And to describe which line we are talking about, we need to know how big the circle is. That is, we need to know the radius of the circle. And we need to know at which point of the circle we are drawing the tangent. That is, how the radius to that point is actually inclined with the x-axis, right? And if I remove the circle now, this particular radius will actually become the perpendicular from the origin to this particular line. So that means the length of the perpendicular from the origin to the line and the angle which that perpendicular makes with the x-axis can describe a line uniquely. And we will use this information to write a new form of equation. And in geometry, if 2 lines are perpendicular, then one line is said to be the normal of the other. So obviously this particular perpendicular that we have drawn from the origin to the line will be the normal to this particular line. And since the information about the line is given in terms of the normal, the equation that we are going to derive here is called the normal form of a line. So let's see what the normal form of a line is. Now these are the 2 lines of information that we know about the line, the length of the normal and the angle which the normal makes with the positive direction of the x-axis. Now let's try to visualize the line first. Say this is the line in the plane whose equation we want to write. Let's drop a perpendicular OA of length P. And the angle which this OA makes with the positive direction of the x-axis is omega. Now we have 4 possibilities of the position of the line where the normal OA can be in either of these quadrants. So that means the angle omega can range from 0 degrees all the way till 360 degrees, unlike the inclination theta which ranges only from 0 degrees to 180 degrees. Right? And our purpose here is to write an equation of this line in terms of P and omega. But how do we find this equation? Well, obviously, we got to make use of the already known forms of the line. Now you can choose to find the slope and a point of the line and apply the slope point form. You can choose to find the 2 intercepts of the line and apply the 2 intercept form, and so on. So obviously you can approach this in 4 different methods. Now let's start with finding the slope. Do we actually know the slope? Well, not directly, but you can actually find it. Now it is said that the line is perpendicular to the normal OA. And if you can find the slope of the normal OA, then you can find the slope of the line, right? Because perpendicular lines have a slopes whose product is -1. Now what is the slope of line OA? Let's try to find its inclination first. In the first 2 quadrants, The line OA has an inclination omega. In the third and fourth quadrant, the line OA has an inclination omega minus 180. So in all these four cases, the slope is nothing but tan theta, right? So it is tan omega. So we get the same slope of the line OA in all these four cases. So therefore, the slope of the particular line should be minus 1 by slope of OA, which is minus 1 by tan omega. And by writing tan omega as sine by cos, you get that the slope of the line is minus cos omega by sine omega. Now we just need to find the coordinates of one point on this line so that we can write the slope point form, right? Now you can choose to find the foot of the perpendicular A, you can choose to find the x-intercept, you can choose to find the y-intercept, right? Anything should work. Now if you notice, OA is the radius of a circle that will be tangential to this line, and it makes an angle omega with the positive direction of the x-axis. So the point A will have coordinates p cos omega, p sin omega, right? And this is true for all these four cases. Now you can simply use this to write the slope point form and you'll get an equation. But let's not do it this way. Let's choose to find the y-intercept, because writing an equation using the slope-intercept form is so easy, right? It is just y is equal to mx plus c. And to find the y-intercept of the line, let's consider one of these cases for convenience. We anyway will get the same answer in all the cases. Now y-intercept is nothing but the length of the segment from the origin to the point where the line meets the y-axis. So to find it, let's consider this right angle triangle where that particular intercept acts as the hypotenuse and the perpendicular OA is one of the legs. If you use some simple geometry, you'll notice that the angle which the y-axis makes with the line is omega. And if you use the definition of sine, you get sine omega is equal to the opposite side by the hypotenuse. The opposite side is OA, which is P, and the hypotenuse is the y-intercept, which is C. So get sine omega is equal to P by C, or C is equal to P by sine omega. So therefore, the y-intercept of this line is P by sine omega. And similarly, if you consider the other right angle triangle, you will get the x-intercept as P by cos omega. So now that you have actually the y-intercept, x-intercept, you can choose to use the two-intercept form to write the equation of the line. But anyways, since we have found the slope, let's use the slope-intercept form, which is y is equal to mx plus c. Now the slope m is minus cos omega by sine omega, and the y-intercept c is P by sine omega. And if you substitute these values, and if you take sine omega to the left-hand side, you'll actually get x cos omega plus y sin omega is equal to P. Now this form of equation, in terms of P, the length of the normal, and omega, the angle which the normal makes with the positive x-axis, is called the normal form of the line. So guys, this is the normal form of the line. Just remember what P and omega are. P is the length of the normal from the origin to the line, and omega is the angle which that normal makes with the positive direction of the x-axis, right? So omega can vary from 0 to 360. Now you should know something about this particular form. Now this form of the line is not valid for two specific lines, the x-axis and the y-axis. Now this is because those two lines do not have a normal from the origin, and they cannot be tangents to a circle that is centered at the origin, right? And even though you actually can substitute P is equal to 0, but still this equation is not valid for that particular two lines. But it's valid for all other lines, even if the lines are vertical, that is, the slopes are undefined. For example, if you have this particular vertical line, then the normal to that line will be purely horizontal, right? So what is omega then? It's 0, right? And the length of the normal, say, is P. So if you substitute omega is equal to 0, you actually get the length of the line as x cos 0 plus y sin 0 is equal to P, which is x is equal to P, right? And we know that that's the equation of any vertical line that is distant P units from the origin. As an example, let's try to find the equation of the line whose perpendicular distance from the origin is 4 units and the perpendicular makes an angle with the negative x-axis that is 60 degrees. So here P is 4 and omega is not 60 because 60 is the angle with the negative x-axis, right? So what is the angle with the positive x-axis then? It's supplementary, right? So it's 180 minus 60, 120 degrees. So now we can use these two to write the normal form of a line. X cos omega plus y sin omega is equal to P. So that is x cos 120 plus y sin 120 is equal to 4. Now since cos 120 is minus half, sin 120 is root 3 by 2, we actually get x minus root 3 by plus 8 is equal to 0. Right? This is the equation of the line which we have obtained using the normal form of a line. So friends, with this normal form of a line, we have covered the 5 forms of the line that are important to us. Now the next time we'll actually consider the algebraic form of the line ax plus b1 plus c is equal to 0, and we'll try to analyze it and read information from it, such as what is its slope, what are the x and the y intercepts, what is the perpendicular distance from the origin, and so on. So until then, let us summarize and you stay curious. Every line in the Cartesian plane except the two rectangular axes can be described as a tangent to a circle that is centered at the origin. The equation of the line having normal distance from the origin p and the angle between the normal and the positive x-axis as omega is given by x cos omega plus y sin omega is equal to p. The normal form of the line is not valid for two specific lines, the x-axis and the y-axis.